This question is from the topic of Bode plot and the subtopic is poles and zeros. The difficulty level of this question is medium. The approximate time required to solve this question is 90 seconds. Given that there is an LTI system and the Bode plot representation for this LTI system is given in the figure. He is asking the number of poles and zeros in the frequency range of 1 to 10 power 7 Hz. Number of poles is represented by NP and number of zeros is represented by NZ. The concept the student should know is Bode plot representation. Application of Bode plot properties in problems is being tested. The shortcut to solve this question is identify the slope change points. So in this given figure, the slope change points are these points. So if you see from this point to this point, that is from 0 to 10 power 1 Hz, this is a straight line. The Bode plot is a straight line. That is, there is no change in slope until 10 Hz. So if you want to find the slope of this point, it is 0 dB per decade because it is parallel to x-axis. Slope of x-axis is 0 and slope of y-axis is infinite. So if you see, this is an inclined line with slope given as minus 20 dB per decade. So if you see the other slope change point, this is other slope change point. So why these are called as slope change point? Because a slope is changing abruptly at this point. So if you see here also the slope is changing, but the change in slope is gradual at the rate of minus 20 dB per decade. But if you see here, there is abrupt change in slope. So if you consider the abrupt change in slope at 10 Hz frequency, just before 10 Hz frequency, the slope is 0 dB per decade, and just after 10 Hz frequency, the slope is plus 20 dB per decade, and hence at 10 Hz it is called as a sudden change in frequency or the slope change point. This type of question is straightforward. Approach is observe slopes in the given Bode plot. The master concept to solve this question is a pole contributes to minus 20 dB per decade and a zero contributes to plus 20 dB per decade. So now if you see here, there is a change in slope at 10 Hz frequency, and the change in slope is nothing but minus 20 dB per decade. So we can conclude that a pole is present at 10 Hz because the reason for this minus 20 dB per decade change in slope is nothing but a pole. A Bode plot is a useful tool that shows the gain and phase response of a given LTI system for different frequencies. The x-axis of the Bode plot is the frequency and the y-axis is the magnitude function. The x-axis is a non-linear scale and y-axis is a linear scale. So Bode plot is generally plotted in a semi-log paper. So it is called as semi-log paper because x-axis is a logarithmic scale and y-axis is a linear scale. Magnitude is dB is plotted in the y-axis. So in y-axis, if you see 1 centimeter, first 1 centimeter corresponds to 10 dB in this graph. So the next 1 centimeter in the graph also corresponds to the same 10 dB magnitude. So 2 centimeters corresponds to 20 dB magnitude. Hence y-axis is called linear scale. But if you see the x-axis, first 1 centimeter corresponds to 10 centimeter. Next 1 centimeter, first 1 centimeter corresponds to 10 Hz frequency. Next 1 centimeter corresponds to 90 Hz frequency. So total first 2 centimeter corresponds to 100 Hz frequency, not 20 Hz frequency. This is because of the logarithmic representation of the x-axis scale, which is a non-linear scale. So if you see here, decade, the term decade is a 10 times change in frequency. So if you see here, from this point to this point, the change in frequency is 10 times. That is, if you multiply 10 by 10, you get 100. If you multiply 100 by another 10, you get 1000. That is, at equidistant intervals, 10 times change in frequency is represented. So now if you want to find the slope of this graph, say we want to find the slope from this point to this point, slope is nothing but delta y by delta x, that is y2 minus y1 by x2 minus x1. So delta y, or the change in magnitude, is 20 dB, which is minus 20 dB because it is decreasing from this point to this point. And the change in x, delta x, is 10 times of frequency. It is like 1000 minus 100, that is 900 hertz frequency, that is 10 times change in frequency, that is a decade frequency. Hence the slope, it is written as hdB per decade. So generally slope is mentioned by the side of this line. Say if it is mentioned as hdB per decade, it means that there is a tenfold increase in frequency. For a tenfold change in frequency, amplitude changes by xdB. Consider a transfer function with only a constant value, means it doesn't have any poles and zeros. Then the Bode plot is nothing but a straight line parallel to the x-axis with slope as 0 or slope as equal to the x-axis. So for every, as we have stated already, for every pole the slope of the line decreases by 20 dB per decade of frequency at that pole's frequency. In this figure, for a 10 times change in frequency, that is here if it is f1, here it is 10 f1. For a 10 times change in frequency, the magnitude is changing by 20 dB, and that is also decreasing from this point to this point. For a 10 times change in frequency, magnitude decreases by 20 dB, that is the slope is minus 20 dB per decade. Hence we can state that there is one pole. If you see the second figure, for the same 10 times change in frequency, the change in magnitude is minus 40 dB. So there are two poles here. So for every pole, the slope of the line decreases by 20 dB per decade, or we can also state it as for every pole, the slope of the line changes by minus 20 dB per decade. Coming to the case of zeros, for every zero, the slope of the line increases by 20 dB per decade, or we can say that the slope of the line changes by plus 20 dB per decade. For a decade change in frequency, for 10-fold change in frequency, the magnitude of the Bode plot curve increases by 20 dB from this point to this point. Hence, we can state that there is 1 zero at this frequency. Now again, for a decade change in frequency, amplitude changes by 40 dB in the second figure. So we can say that the slope is 40 dB per decade. That is, at this point, the slope change of 40 dB occurs, because in this line the slope is 40 dB per decade. In this line the slope is 0 dB per decade. So the change in slope at this frequency is 40 dB per decade. As it is 40 dB, and we know that 1 zero corresponds to only 20 dB. So as it is double change the slope, we can state that there are two zeros at this frequency. So clearly the x-axis is represented with the frequency ranges. 10 power 1 means 10 Hz, 10 power 2 means 100 Hz, 10 power 3, 10 power 4, and this is 10 power 7 Hz. He is stating that find the number of poles and zeros for the system given in the question, which is an LTI system, and that LTI system is represented by this Bode plot. Instead of giving a system can be characterized by transfer function, differential equation, Bode plot, root locus plot, Nyquist plot. Instead of giving the transfer function of the system, he has given the Bode plot of the system. If transfer function is given directly, we can find the number of poles and zeros by observing the numerator and denominator. But he has given the Bode plot and asking to find the number of poles and zeros. In this frequency range of 1 to 10 power 7 Hz. So if you see, this is 10 power 7, 1, this is 0, this is 10 power 1, means 1 will be somewhere around here in this region. So from this frequency to this frequency, he is asking us to find the number of poles and zeros. So the basic hint to solve this question is, whenever a pole or a zero occurs in this frequency range, then at that point in the Bode curve, a change in slope occurs. So if you see here, it is a straight line parallel to x-axis. There is no change in slope until this point, until the point of 10 Hz. At 10 Hz, there is a change in slope. Here the slope is 0 dB per decade. Here the slope is minus 20 dB per decade. Just below 10 Hz, the slope is 0 dB per decade. And just after 10 Hz, the slope is minus 20 dB per decade. So the change in slope is minus 20 dB per decade. So this is a slope change point. Likewise, slope again changes at 10 power 2 Hertz. Another slope change point is 10 power 3 Hertz. So these all are the slope change points. It means that at these points there is either a pole or a zero, and hence the slope is changing. Say consider 150 Hertz. It will be somewhere around here. It will be in between 100 Hertz and 1000 Hertz. Here there is no slope change, so there is no pole or zero. Consider 1001 Hertz, so it will be somewhere around here. So here also there is no slope change point. So it means that there is no pole or zero at this point also. So we will consider the first slope change point, which is at 10 Hertz. So at this point the change in slope is minus 20 dB per decade minus 0 dB per decade, which is minus 20 dB per decade, and we know that one pole contributes to minus 20 dB per decade. So at 10 Hertz there is one pole. So consider the next slope change point, which is 10 power 2 Hertz or 100 Hertz. At 100 Hertz, just before 100 Hertz, the slope is minus 20 dB per decade, and just after 100 Hertz, the slope is minus 60 dB per decade. That is, the slope is changing from this value to this value. So the change in slope is equal to new slope minus old slope. That is minus 60 minus of minus 20 is equal to minus 60 plus 20 is equal to minus 40 dB per decade. We know that one pole corresponds to minus 20 dB per decade slope only, but here minus 40 dB per decade slope is there. It means that there are two poles at 100 Hertz. Likewise, at 10 power 3 Hertz, the change in slope is plus 20 dB per decade. We know that 1 0 corresponds to plus 20 dB per decade, and hence at 1000 Hertz there is 1 0. Likewise, we have to calculate at all the slope change points. At 10 power 4 Hertz, change in slope is 0, new slope, old slope is minus 40 dB per decade. The difference is plus 40 dB per decade. Hence there are two zeros. Now, at 10 power 5 Hertz, the change in slope is minus 40 dB per decade. Minus 0 is equal to minus 40, which corresponds to two poles. At 10 power 6 Hertz, the change in slope is minus 60 minus of minus 40 is equal to minus 60 plus 40 is equal to minus 20, which corresponds to one pole. So if we count all the poles and zeros, we get 6 poles and 3 zeros are present from this point to this point. Thank you.